Right now, as you read this, there is a piece of metal sitting inside the bodies of hundreds of millions of living people, fused directly into their bones, and their bodies have absolutely no idea it is there. Not a single immune reaction, not a trace of rejection, nothing. The bones simply grew around it, through it, into it, as if the metal had always been part of the skeleton, as if it belonged there from the very beginning. And the strangest part is not that this is happening. The strangest part is where this metal actually came from before it ended up inside a human body. Because it did not come from a mine, not exactly. It came from an explosion so enormous, so violent, so incomprehensibly hot, that our entire solar system did not even exist yet when it happened. The metal inside the hip of your neighbor, your parent, maybe you, was forged inside a dying star billions of years before Earth was formed. It drifted through cold, empty space. It settled into rocks. It waited. And then we dug it up, melted it down, shaped it, and put it back inside living bodies. And the bodies said nothing. They just accepted it. That single fact alone should stop you in your tracks, because it means we have been living alongside one of the most extraordinary substances in the history of the universe, and almost none of us know its real story. We know the name, titanium, element number 22, but the name is just the surface. Underneath that surface is a story that stretches from the death of stars to the inside of hospital operating rooms, from Cold War spy operations to the food sitting in your kitchen cabinet right now. And every layer of that story is stranger than the one before it. I want to take you through all of it, because once you understand what titanium actually is and what it actually does, you will never think about the material world the same way again. We tend to assume that the things we build and use are separate from us. Tools exist outside the body. Machines stay on the other side of the skin. That line felt natural, obvious, not even worth naming. Titanium quietly erased it. Not through force, not through some dramatic technological breakthrough that made headlines. It erased that line through chemistry. Through the simple, invisible fact that its surface behaves in a way that 400 million years of immune system evolution never learned to recognize as a threat. And so the body let it in and kept it, permanently. We are going to start not with the history, not with the science, but with the biology. Because that is where the story becomes genuinely hard to explain. Friends, if this is already making you think differently about the world around you, subscribe and leave a like. It genuinely helps this kind of content reach more people, and there is a lot more ahead that you do not want to miss. Here is something worth understanding about your immune system before we go any further. It is not rational. It was never designed to be rational. It was designed to be paranoid, fast, and merciless. Because in the environment where it evolved, hesitation meant death. Your immune system will mount a full inflammatory response around a tiny wooden splinter that poses essentially no chemical threat whatsoever. It will attack its own perfectly healthy tissue in autoimmune conditions, mistaking the familiar for the foreign. It will flood your sinuses and make your eyes water because of pollen, which is chemically harmless to almost everything it touches. This system was sharpened over hundreds of millions of years into something with almost supernatural sensitivity for detecting anything that does not belong inside the body. And then you put a piece of titanium into living bone, and the whole system goes completely quiet. Not temporarily, not while the body is in shock from the surgery, permanently. You could check that same joint 30 years later and find zero signs of immune response, zero chronic inflammation, zero tissue breakdown around the metal. Other metals do not behave this way. Stainless steel in the body causes slow, persistent inflammation. Certain alloys used in older implants were found to gradually release microscopic metal ions into the surrounding tissue, ions that showed up in blood tests. Ions that the immune system absolutely did notice and responded to. Even nickel, which is in countless everyday objects, triggers allergic reactions in a significant portion of the population when it stays in contact with tissue long enough. But titanium sits there in silence. Total, complete biological silence. The reason comes down to something you cannot see with any standard microscope. The moment titanium is exposed to oxygen, and we are talking about a reaction that happens faster than you can blink, it forms a thin layer of its own oxide on the surface. This layer is somewhere between 2 and 6 nanometers thick. To give you a sense of how thin that is, a single human hair is roughly 80,000 nanometers wide. This oxide film is not even a coating in any meaningful visual sense. It is a shell of chemistry, just a few dozens of atoms deep, sitting on the surface of the metal like an invisible second skin. And that shell is what changes everything. The immune system never actually touches the titanium. It touches the oxide. And titanium oxide is biologically inert in a way that is almost unique among materials we have learned to work with. It does not release ions. It does not interact with the proteins in blood plasma. It does not trigger the specialized cells that the body sends in to investigate and destroy foreign objects. To the immune system, the oxide surface reads as something close to mineral, something geological, something that has no business being attacked. So the body does not attack it. But then something happens that goes even further than simple tolerance. Something that took scientists decades to fully appreciate. The bone does not just leave the metal alone, it grows into it. Living bone cells attach to the titanium surface and begin building new bone matrix directly along the metal, filling in every microscopic texture and irregularity on its surface. After enough time, you cannot separate the implant from the bone without destroying the bone itself. They have become a single structure. That is not a prosthetic. That is integration at a level that blurs the line between the biological and the inorganic in a way we still do not fully understand at the molecular level. And here is what makes this even more remarkable. We have been using this phenomenon clinically for decades. We have built an entire global medical industry on top of it. And the precise chain of biochemical events, the exact molecular conversation between a titanium oxide surface and the living bone cell that triggers this process, is still an active area of research. We use it. We rely on it. Millions of people are alive and walking because of it, and we cannot fully explain it yet. So the next question is obvious. How did we even discover this was possible in the first place? And the answer to that is one of the best accidental discoveries in the history of science. The greatest medical discovery of the 20th century was made by a man who was not even trying to make a medical discovery. He was not looking for a breakthrough. He was not running trials on implants or prosthetics. He was doing something far more ordinary, tracking how blood moves through tiny vessels inside living bone tissue. A question so narrow and technical that most people outside his specific field would struggle to explain why it even mattered. His name was Dr. Eric Sandmark, and he worked at a research institute in a cold northern city where the winters lasted half the year and the laboratory windows fogged up from the inside before noon. He was methodical, quiet, the kind of scientist who filled notebooks with small, careful handwriting and rarely raised his voice at conferences. And one afternoon, in the middle of what should have been a completely unremarkable series of experiments, he stumbled onto something that would eventually change the lives of hundreds of millions of people. He had been implanting tiny observation chambers into the leg bones of animals to watch blood circulation up close. The chambers needed to be made of something structurally stable, something that would hold its shape under pressure and not interfere too aggressively with the surrounding tissue. Titanium seemed like a reasonable choice. Nobody attached any special significance to that decision. It was a technical detail, the kind that gets one line in a methods section and nothing more. Months passed. The circulation data came in. The observation series reached its end, and then Sandmark went to retrieve the chambers. They would not come out. He tried carefully at first, then with more force, then with the kind of controlled frustration that scientists use when equipment fails at the worst possible moment. Nothing. The bone had grown into the metal so thoroughly, so completely, that the two had become one continuous structure. Separating them would have meant destroying the bone entirely. Any other researcher in that room might have felt the specific cold sinking feeling of a ruined experiment. Might have written it off as contamination, or a problem with the chamber design, or just bad luck. Sandmark did something different. He sat with the problem. He looked at it from the other direction. He asked what the experiment would look like if this was not a failure at all, but a finding. That single shift in perspective is the reason you have neighbors and relatives walking around today with functional joints that their bodies have accepted completely and permanently. But before any of that could happen, Sandmark had years of quiet, unglamorous work ahead of him, and the world was not going to make it easy. He spent the years that followed doing what good scientists do when they find something they cannot explain. He tested it every way he could think of. He changed the surface texture of the metal. He varied the duration of contact before attempting retrieval. He worked with different bone sites, different conditions, different animals. He was not trying to prove a theory. He was trying to understand a phenomenon that had no name yet and no framework. The results were consistent. Every time. Bone did not just tolerate titanium, it actively integrated with it. The metal became structural. Not a foreign object in the tissue, but part of the tissue itself. By the time Sandmark felt confident enough to move toward a human application, he had a patient in mind. A man named Carl, a construction worker in his 40s who had lost most of the functional use of his lower jaw due to a severe injury sustained years earlier. Conventional approaches had been tried and had not held. Carl could not chew properly. Speaking was difficult. He had lived with this for long enough that he had stopped expecting solutions. Sandmark proposed placing titanium anchors directly into the jawbone, anchors that would fuse with the bone and provide a stable base for a fixed prosthetic. Carl agreed, not with great enthusiasm, but with the quiet acceptance of someone who has run out of better options. The procedure went as planned. The weeks that followed were unremarkable, which was exactly the point. No swelling beyond normal healing, no rejection. No chronic pain around the implant sites. The bone grew in, the anchors held. Carl could eat again, properly, without pain, without the prosthetic shifting or loosening. He kept those implants for the rest of his life, decades. And when Sandmark stood in front of an international audience of surgeons and dental specialists and presented all of this, the clinical records, the long-term follow-up, the histological evidence of full bone integration, the room did not erupt in applause. It responded with polite, firm, professional skepticism. The specialists sitting in those chairs had spent their careers working within a system built around removable solutions. Permanent metal in living bone sounded either like an exaggeration or like a poorly controlled experiment. One of them asked, with genuine condescension, whether Sandmark had considered that his results might simply reflect an unusual patient population. Another suggested the methodology needed independent verification before anyone could take clinical implications seriously. Sandmark stood at the podium and answered every question without raising his voice. He had the data. He knew what the data said. And somewhere in that room, behind the skepticism and the institutional caution, a few people were listening very carefully. Because the data was too clean to dismiss entirely, and everyone in that room, even the loudest skeptics, knew it. Every atom of titanium that has ever existed on this planet was born inside a dying star that exploded before our sun had even formed. Let that sit for a second. The metal that Sandmark placed into Carl's jawbone, the metal that fused with living bone and held for decades, did not originate on Earth. It was not here when Earth formed. It arrived as part of the raw material that gravity pulled together to build this planet. Material that had already been through one complete stellar life cycle before ours even began. And we know this not as a theory or a comfortable scientific assumption, but as a directly observed, instrumentally measured fact. Here is how it works. When a star much larger than our Sun reaches the final stage of its life, something happens in its core that is almost impossible to picture in human terms. The temperature climbs to around 3 billion degrees. For comparison, the center of our own Sun sits at about 15 million degrees. So we are talking about conditions that are roughly 200 times more extreme than what powers all the light and heat this planet has ever received. At those temperatures, atomic nuclei that would never interact under normal conditions are forced together with enough energy to fuse. This process produces a specific family of elements, and titanium is one of them. The whole thing lasts about 1 day. After millions of years of the star burning steadily, the final act takes 1 day. Then the core collapses under its own gravity in a fraction of a second. The outer layers slam back against it and rebound outward at a speed that is a measurable fraction of the speed of light. And everything that was synthesized in that core, including the titanium, gets scattered across hundreds of light-years of space. This is not a poetic description. Astrophysicists have observed it directly. There is a stellar remnant in our galaxy, the glowing debris cloud left behind by a massive explosion that occurred a few centuries ago by our calendar. Scientists working with space telescope data detected a specific radioactive form of titanium inside that remnant. This particular form decays relatively quickly on cosmic timescales, meaning the only way it could still be present in detectable quantities is if it was created at the moment of the explosion itself. Not billions of years ago, at that specific event. That is a direct observation of titanium being born. And the atoms that are right now fused into someone's jawbone or hip socket went through exactly that process, just in a different star, a different explosion, billions of years before this solar system existed. That fact changes the scale of everything we have been talking about. Sandmark's discovery, Carl's jaw, the biology of osseointegration, the global implant industry, all of it sits on top of a 4.5 billion-year journey that started with fire and pressure and death on a scale our brains genuinely cannot process. But here is where the story gets stranger, not cosmically strange, but humanly strange. Because the path from that stellar explosion to a usable piece of metal in a surgeon's hand was almost comically difficult. And the people who got us there are names almost nobody knows. The first chapter of that story begins not in a laboratory, not in a university, but in a riverbed. A man named Thomas Greer was walking along a shallow river in the rural southwest of England sometime in the late 1700s. He was an amateur in the truest sense of the word. He had a day job that had nothing to do with chemistry or geology. He collected minerals the way some people collect stamps, out of genuine curiosity with no institutional backing and no academic reputation to protect or promote. He found a deposit of unusual dark sand near the water's edge. It was heavy for its volume, and it behaved oddly around a magnet, which immediately suggested iron content. But when he took it home and ran it through the chemical analysis methods available to him at the time, something did not add up. Yes, there was iron oxide in the sample, but there was also another oxide, white, unlike anything in the reference literature he had access to. He could not identify what metal it belonged to. He wrote up his findings carefully and honestly, published them in a small regional scientific journal, and gave the unknown compound a name derived from the valley where he had found it. Nobody responded. The publication sat in a drawer of scientific history and collected dust. A few years later, a well-connected German chemist working in a major European city independently extracted the same unknown oxide from a completely different mineral source brought to him from Central Europe. He had a prestigious position, an established reputation, and a wide network of colleagues who paid attention when he published. He named the new element after the ancient primordial gods, figures of mythology who existed before the organized world, vast and ungovernable. The name stuck. The original discoverer was not credited in the moment, and neither of them, Not Greer, not the German chemist, ever actually held pure titanium metal in their hands, because extracting the metal itself turned out to be a problem that would resist solution for the next century and a half. For over 150 years, the brightest chemists in the world tried to pull pure titanium out of its minerals and failed every single time. Not because they lacked intelligence, not because the chemistry was unknown, but because titanium has a property that makes it almost sadistically difficult to work with. The moment it gets hot enough to process, it stops being a passive material and becomes something closer to a chemical predator. It pulls oxygen out of the air with a grip that nothing short of a vacuum can break. It absorbs nitrogen, it drinks in hydrogen, and every impurity it swallows turns it from a promising structural metal into a brittle, crumbling, useless mass. The best chemists of the 1800s got titanium to about 80% purity and called it a partial victory. By the early 1900s, someone managed to push that to around 98% in a sealed steel container, which was genuinely impressive for the time, but still not clean enough for any serious engineering application. The metal sat in this strange purgatory for generations. Abundant in the earth, theoretically extraordinary in its properties, but practically untouchable. A ghost of a material. Known by name, impossible to actually use. The man who finally solved this was not a famous academic. He was an engineer from a small country in Central Europe, a quiet, precise man named Heinrich Voss, who had spent years working on metallurgical problems that most of his colleagues found too stubborn to bother with. Voss understood something that the researchers before him had not fully acted on. The problem was not the chemistry of the reduction reaction itself. The problem was the assumption that you could manage titanium's reactivity rather than eliminate contact with the atmosphere entirely. Previous approaches tried to work fast, or use clever reducing agents, or create conditions where the metal would not have time to absorb contaminants. Voss decided that hot titanium and open air could never be in the same room, not for a second, not at any stage of the process. His solution had two steps, and the genius was in how completely he sealed each one. First, he converted the ore into a liquid intermediate compound by reacting it with chlorine gas at high temperature. This produced a colorless liquid that fumes aggressively when it touches moisture in the air, a liquid with a sharp chemical smell that coats the inside of your nose if you get anywhere near it without protection. But it could be purified by distillation to a very high degree of cleanliness, which meant the titanium going into the next step was already stripped of most of its natural impurities. Then this purified liquid was loaded into a sealed steel reactor. The air was pumped out completely. Inert gas was introduced. Molten magnesium was added and heated to around 850 degrees. Magnesium is chemically aggressive enough to strip the chlorine away from the titanium compound, but it does not react with titanium itself. The titanium precipitates out of the reaction as a porous, spongy solid, gray and rough to the touch, sitting inside the sealed reactor like a mineral formed in a cave. The reactor was cooled, opened, the sponge extracted, cleaned, and then remelted in a vacuum arc furnace, where electrodes strike an arc in a copper crucible that never itself reacts with the metal. Pure titanium. For the first time in history, reliably, repeatedly, at a scale that could actually mean something. When the war in Europe forced Voss to leave his home country and relocate to North America, he arrived carrying his process documentation and very little else. He approached a government materials bureau that was, at that moment, under considerable pressure to find new structural materials for military applications. They gave him a facility and funding. Within a few years, he was producing several kilograms of pure titanium per week. Within a decade, industrial-scale production had begun. And here is the part that should genuinely surprise you. The process Voss developed is still the primary industrial method for producing titanium today. Not a modified version of it. Not a descendant of it with a new name. Essentially the same process, refined in its engineering details but identical in its logic. We have quantum computing research, gene editing, artificial intelligence, and we still make titanium the same way a displaced European engineer figured out before the middle of the 20th century. Because nothing that has been proposed since has managed to be both cleaner and economically viable at industrial scale. That fact alone tells you something important about how genuinely difficult this metal is to work with. But the story of how titanium entered the modern world does not stop with Voss and his reactor. Because almost simultaneously, on the other side of the planet, in a country that was rapidly becoming the most significant geopolitical rival the West had ever faced, scientists working independently arrived at a nearly identical process and began their own industrial production. Two countries, two processes, almost the same solution reached at almost the same time, without any communication between them. And what each of those countries decided to do with the metal next is where the story takes a turn that is genuinely difficult to believe. The reconnaissance aircraft was designed to be invisible not to radar, but to physics itself. The engineers were not trying to hide it. They were trying to make it so fast that hiding was unnecessary, because nothing in existence could get close enough to matter. The target speed was roughly 3.5 times the speed of sound. At that velocity, the air pressing against the aircraft's skin generates heat through friction alone. Heat measured not in tens of degrees, but in hundreds. Aluminum softens and loses its structural integrity well below those temperatures. Standard steel is strong enough at heat, but far too dense, too heavy to reach those speeds and altitudes in the first place. The engineering team working in a classified facility on the western coast of North America needed a material that was simultaneously light enough to fly, strong enough to hold its shape under extreme mechanical stress, and stable enough not to deform or weaken at temperatures that would destroy conventional airframe materials. There was only one answer: titanium. Roughly 85% of the entire airframe would be built from titanium alloys. It was an aircraft unlike anything that had been constructed before. And building it turned into a technological war against the metal itself. Standard cutting tools wore out at several times the normal rate when machining titanium. Engineers had to develop entirely new tooling. Finished parts cracked in the workshop for reasons nobody could immediately explain. The investigation eventually revealed that the ordinary tap water used to rinse the machined components contained trace amounts of chlorine, and when those components were subsequently heated, the chlorine reacted with the titanium at a microscopic level, creating stress points that propagated into visible fractures. The entire facility switched to distilled water for every cleaning operation. Pencil marks directly on the metal surface were prohibited, because graphite reacts with titanium under heat and forms brittle spots. Any fixture or fastener with a cadmium coating was removed from the process entirely, because cadmium causes a specific type of internal cracking in titanium when the two are heated together. In summer, when the California workshop air temperature rose, the metal blanks expanded just slightly more than the machining tolerances allowed for, and parts came out fractionally oversized. The processing parameters had to be adjusted by season. Each of these problems cost weeks of investigation, adjustment, and retraining. The learning curve was not a curve. It was a wall that the engineering team climbed one handhold at a time. But the aircraft flew. It flew faster than any weapon system of its era could intercept. During its entire operational service life, not one was ever destroyed in flight during active operations. And here is the detail that still feels almost too absurd to be true. A significant portion of the titanium used to build this aircraft came from the one country it was specifically designed to spy on. The procurement problem was straightforward and brutal. Direct purchase of strategic materials from a geopolitical adversary was impossible through any official channel. So intelligence operatives set up a network of trading companies registered in neutral countries. Companies with unremarkable names and no visible connection to any government or defense contractor. These companies placed routine commercial orders for titanium through standard trade channels. The metal was shipped, transferred through intermediaries, and quietly delivered to the facility where the aircraft was being built. The country on the other side of that trade never knew where its material was going. It filled the orders efficiently and on schedule. Because as far as its records showed, it was simply selling industrial metal to civilian buyers in neutral markets. Its own titanium, produced in its own facilities by its own workers, was being shaped into the airframe of a machine that would spend years flying over its own territory at altitudes and speeds its defense systems could not touch. That is not a metaphor. That is simply what happened. You have been eating a compound of titanium for decades, and nobody told you. Not as contamination, not as an accident, but as a deliberate additive approved by regulators, listed on ingredient labels under a code number that most people scroll past without a second thought. A white powder, tasteless, odorless, chemically described as titanium dioxide, was added to food for one single reason: to make it look whiter. Chewing gum, candy shells, the icing on celebration cakes, the coating on pharmaceutical tablets, the powdered creamer in the break room at your office. For decades, the logic behind its approval was essentially this: people have been consuming it for years, and nobody has visibly collapsed, so it is probably fine. That was the standard of evidence. Nobody dropped immediately, therefore safe. Then a major European food safety authority completed a full scientific review of the additive and published a conclusion that landed like a quiet earthquake in the food industry. The conclusion was not that the substance was definitively harmful. It was something in some ways more unsettling. It was impossible to establish any daily intake level that could be guaranteed safe over years and decades of regular consumption. The specific problem was nanoparticles. Any commercial batch of this compound always contains a fraction of particles small enough to behave by completely different rules than larger particles of the same substance. Particles at that scale can cross biological barriers that are completely impermeable to larger versions of the same material. Laboratory studies included in the review showed that these nanoparticles, when in contact with living cells, were capable of entering the cell nucleus and interacting with DNA in ways that raised a formal concern about long-term genetic damage potential. The authority used the term genotoxic potential in its published conclusion. That phrase does not mean the substance definitely causes harm. It means the available evidence cannot rule it out. And when you cannot rule out DNA-level damage from something people consume every day, you cannot set a safe dose. So the substance was banned from food across an entire major regulatory region. Manufacturers were given a transition period, and then it became illegal to include it in food products sold in that market. In most of the rest of the world, including large and heavily populated countries, it remains fully legal and in active use right now. The regulatory positions are not slightly different. They are directly opposite. The same compound, the same nanoparticle concern, the same published science, and two completely different official conclusions depending on which side of a border you are standing on. That tension has never been publicly resolved. And while that debate continues, the exact same titanium dioxide compound, in a different physical form and at a completely different scale of application, is being used to save lives in hospital operating rooms. Not by being swallowed, by being painted onto surfaces and activated by light. The same element that built the fastest spy aircraft in history, that fused with Carl's jawbone and held for decades, that was forged in a stellar explosion before Earth existed, is right now doing something in a Tokyo hospital corridor that would have sounded like science fiction 30 years ago. A research team studying semiconductor chemistry in the early 1970s noticed something unexpected while working with titanium dioxide as an electrode material in water. When they exposed the electrode to ultraviolet light, the water began splitting into hydrogen and oxygen without any external electrical input. Just light hitting the surface of the material, and the chemical reaction started on its own. The mechanism involves the way titanium dioxide responds to photons of sufficient energy. When a photon hits the surface, it knocks an electron loose, creating a pair of charged particles, a free electron, and a positively charged gap. That gap has an extraordinarily strong oxidizing potential. It pulls electrons from water molecules nearby, producing hydroxyl radicals, which are among the most chemically reactive particles in chemistry. These radicals attack and break apart organic molecules on contact, reducing them to carbon dioxide and water. The practical implication of this took some years to fully appreciate, but once it did, the applications moved fast. A thin layer of titanium dioxide applied to a surface becomes, under light, a continuous machine for destroying organic contamination. Bacteria land on a hospital wall coated with this material, and they are broken down at the molecular level by radicals generated from the room lighting. No chemicals sprayed, no manual disinfection required. The surface does it passively, continuously, using light that is already there. Studies demonstrated this effect against a range of pathogens, including strains that have developed resistance to conventional disinfectants. During the period of heightened concern about airborne pathogens in enclosed spaces, photocatalytic titanium dioxide filters were developed for ventilation systems that could break down organic particles moving through the airflow. Self-cleaning glass using the same principle has been installed on the facades of office buildings, airports, and hospitals across Europe and Asia since the early 2000s. The same property that generates hydroxyl radicals on a surface is also being investigated for direct medical use. Titanium dioxide nanoparticles can be delivered into tumor tissue and then activated by a light source guided through optical fiber. The radicals they generate destroy cells from the inside. Because the nanoparticles are concentrated in the tumor and not in the surrounding healthy tissue, the destruction is selective. Early clinical trials in bladder and skin cancer models have shown results significant enough to continue the research. This is not yet standard treatment, but it is no longer theoretical. And sitting underneath all of this, underneath the hospital coatings and the cancer research and the self-cleaning glass, is the same chemistry that makes titanium biologically invisible inside a living bone. The oxide surface, the inert shell, the thing that fools the immune system. Humanity learned to use that property to save joints. Now it is learning to use it to save lives in an entirely different way. And that brings us to where this story actually ends, or rather, where it stops having an ending at all. We are living right now at the moment where the boundary between the biological and the inorganic is not being debated, but dismantled, quietly, procedure by procedure, in operating rooms and research labs around the world. A person with a titanium hip joint has metal that is structurally fused to their skeleton. A person with a titanium-cased pacemaker has a device that controls the rhythm of their heart, a device without which the heart stops. A person receiving deep brain stimulation for a neurological condition has electrodes inside their brain tissue connected to a titanium-housed controller sitting under their skin. And now, patients with severe paralysis are receiving neural implants in titanium casings with hundreds of electrodes inserted directly into the motor cortex, allowing them to control computers and external devices using only the electrical signals their brain produces when they intend to move. These are not experimental curiosities. These are clinical realities happening right now to real people with documented outcomes. The titanium that was born in a dying star, that drifted through space for billions of years, that resisted human attempts to extract it for a century and a half, that a quiet researcher accidentally discovered could fuse with living bone, is now sitting inside human nervous systems and helping paralyzed people interact with the world. We did not plan this trajectory. We did not sit down and decide that one day we would build permanent inorganic components into living human bodies. We followed the chemistry, one small discovery at a time, and the chemistry led us here. Every atom of titanium currently fused into a living skeleton will outlast that person by geological timescales. It will return to the soil. Over millions of years, it will cycle back into rock. Eventually, when our sun expands and the inner planets are consumed, it will return to space. The same journey it has already made once. And here is the thing that stays with me. We talk about using titanium, but titanium was here before us, will be here after us, has survived conditions we cannot physically experience, and has quietly integrated itself into the structure of our bodies in a way that our most sophisticated biological defense system cannot detect or reject. So here is the question I want to leave you with, and I genuinely want to know what you think. If a material is permanently fused to your skeleton, regulating your heartbeat and reading your neural signals, at what point does it stop being a tool you are using and start being part of what you are? Write your answer in the comments. I am not sure there is a right one. If this story changed the way you think about the world around you, leave a like and subscribe. There is no better way to tell me that this kind of content is worth making.